Hi everybody, I'm Daniele Zanato, Sales Manager at LaserPoint, and the topic of today's webinar is the new blink high speed, which we consider the new metrological standard in ultrafast laser measurement. LaserPoint is a manufacturer of laser power and energy sensor. We have a wide portfolio of more than 100 different kind of sensor. We have a specific product line developed for measuring and characterizing ultrafast laser with pulse duration down to the femtosecond and repetition rate up to the megahertz range, which is actually the topic of today's webinar. And for more than 30 years, LaserPoint has provided solution for power and energy measurement to different kind of customers, from OEM to industrial, medical, and scientific. Our products are especially recognized for their accuracy and reliability. Here is a quick overview and summary of today's webinar. First, we are going to have a look at the new Blink HS sensor and its electronics, the HSM1000 electronics. We are actually performing an experiment. We are measuring a real fiber laser emitting an average of 20 watts, 980 kilohertz and 4 nanoseconds with our Blink HS sensor. Finally, we are going to have a look at the application and the benefit of the new Blink HS. This is the Blink HS sensor. As you can see, I have reported some of the most important specifications. It can measure an average power up to 20 watts. This is a water-cooled device. Being based on a thermal design, the absorber have a wide and broad spectral range from 250 nanometer up to 11 micrometer. The maximum energy that can be measured with the device is 10 millijoule, and the minimum energy is 1 microjoule. The repetition rate can go up to 1 megahertz, although we are now developing a new device that will be even faster than this one. This is the water-cooled model. We do have also a fan-cooled, forced air-cooled device, which is the BMA 15W 14T. This one has mainly the same specification as the water-cooled one, with the only difference being the maximum average power that is limited in this case to 15 watt. Finally, we have also a device which is not cool at all, meaning that is conduction cooled, and in that case the maximum average power that can be measured with that device is 5 watts. This is the HSM1000, which is the electronics that we have specifically developed for the Blink HS sensor. It is capable of sampling up to 500 megasample per second with a bandwidth of 250 megahertz. It connects to Ethernet to the computer for faster data transfer. It has got a triggering and trigger out output in order to allow closed loop process control. It can work in different modality. We have the oscilloscope mode, the two metrological mode, which are the pulse energy and the real-time measurement. It is possible to perform pulse-to-pulse statistical analysis of the measurement performed with the device. And of course, it is possible to export data and reports. We have developed a specific graphical user interface, which is the Giotto. And finally, here are the dimensions: 182, 162, 57 millimeter. This is the current status as far as the power and energy sensor. There are three main different technologies, which are the thermopiles, the pyroelectrics, and the photodiodes. The thermopiles sensor are capable of measuring high power, much more than 1 watt. They have a broadband operation. They can measure CW laser, of course, And for pulsed laser, they provide the average power. We then have the pyroelectric sensor, which are specifically developed typically for pulsed laser. In fact, they cannot usually measure CW laser, but of course they can measure pulsed laser with average power more than 1 watt. They have a broadband operation, and they have a limited speed capabilities. In fact, typically they can reach up to 20 kilohertz and no more. Finally, we have the photodiodes, which are very fast. In fact, they can measure pulsed laser even at high repetition rate, but they have a very low saturation threshold. In fact, with a photodiode, usually you can measure up to some hundred of milliwatts. Also, they do not have a broadband operation because the operation wavelength depends on the specific semiconductor that is used for the photodiode. Here it is how those technologies compare with our new Blink HS sensor. First, the Blink HS sensor is capable of measuring high power. At the moment, we can go up to 20 watts with our water-cooled device. We are planning to increase this value in the future. Being based on a thermal design, they have a broadband operation. They are capable of measuring both pulsed and CW laser, and for the pulsed laser they can reach at the moment up to 1 MHz repetition rate. This is the specific measurement setup. As you can see, we have the Blink HS sensor on the right, the HSM 1000 electronics that is connected to the sensor with an RF cable, and finally the electronics is connected to our computer or laptop via Ethernet connectivity for a fast data transfer. For the measurement, as I mentioned before, today we are performing a live measurement of a real fiber laser, which is emitting at 1070 nanometer with a repetition rate of 980 kilohertz. The pulse duration is 4 nanoseconds, and the maximum average power for this laser is 20 watt. And we are performing a characterization and measurement of this fiber laser with our Blink HS sensor. Actually, I'm going to show you right now the real setup here on my left. Here at my left, you can see the experimental setup for the measurement. We have a fiber laser, as I mentioned, that can go to a maximum average power of 20 watts. The laser is emitting from the top, and at the bottom we have the sensor, the Blink HS sensor, and here we have the HSM 1000 electronics. This is a closer look at the Blink HS sensor below the laser. As you can see here, we have the red pointer pointing to the center of the sensor. This is a water-cooled device, so we have the pipes for the water, and this is the IROS connectors that goes to the HSM 1000 electronics. And now we have a look at the Giotto software, which is the specific graphical user interface that we have developed at LaserPoint for the Blink HS. When we launch the software, the Giotto software, the first operation to be performed is the authentication of the device. That can be done by clicking on the top left button, authentication here. If everything is working fine, we should get an authentication OK message in green here on the left, meaning that the software has been able to authenticate the instrument connected to the computer. On the bottom left, we have a series of green LEDs. These LEDs can be green, yellow, or red. In order to be sure that the software is working correctly, all the LED must be green. As you can see, there is one for the warm-up, and then there are some alarm status. Also, there is the temperature of the hardware, of the HSM 1000 electronics, and the temperature of the sensor that are displayed here. There is a more detailed diagnostics status of the device by clicking to the diagnostics button here on the right. As you can see here, all checks are okay, meaning that everything is working correctly. There is a board check, a check for the hardware, for the head, and finally some information about both the hardware and the software. I go back to oscilloscope mode. So we have successfully authenticated our instrument. The first thing we need to set is the laser parameters in order to perform an accurate measurement. This can be done by pressing the setup on the top. As you can see, there are two fields, one indicated at laser type. In this field, we are going to select the pulse duration of the laser that we are going to measure. In our case, it is a nanosecond laser, so the correct selection would be nano. But as you can see, there are other options like pico for picosecond laser, femtosecond, and microsecond laser. So we select the nanosecond laser. And finally, we also have to select the wavelength of the laser we are going to measure. This specific system, this specific sensor, has been calibrated at 1064 nanometer and 355 nanometer. We are measuring a fiber laser emitting at 1064 nanometer, so we select here 1064. And now we are ready for the measurement. As you can see here on the right, there are three different modalities of operation. The first one that we are going to look at is the oscilloscope mode, but there are two additional modalities, which are the real-time parameters and the pulses parameter. When we first connect and launch the software after the authentication, what we can do is go to the oscilloscope mode and start the acquisition. Now the laser is not running, so I expect to see just noise, thermal noise coming from the sensor. Here we have a bar, a progressing bar showing the progression of the measurement, and as you can see here, we have the measurement performed by the system. It is, as you can see, just pure noise because the laser is not running at the moment. As you can see, there are three different levels shown here, one in blue, one in red, and one in green, that can be specified on the hardware setting here. The blue line is the baseline, the trigger start is the green line, and the trigger stop is the red line. These levels are used in order to perform a correct measurement. The baseline is basically our zero, the zero for the sensor, so it should be positioned more or less at the level of the noise that we have just measured. The trigger start and the trigger stop levels are used as the trigger start, meaning that the pulse measurement will start at that level and will stop at the level of the trigger stop. All these levels can be adjusted manually, like I'm doing now. In order to perform a correct measurement, we need to properly set the values for these levels. There is an automatic procedure that the software can perform automatically, and it is done by pressing auto setup here. So if we press auto setup, we will see that there are some calculations. The system will perform another measurement of the noise. This operation has to be performed without the laser on, so with the laser off. And now, as you can see, the three levels have been shifted appropriately. The baseline has been positioned more or less in the middle of the noise. The trigger stop has been positioned just above the noise level, and the trigger start has been positioned at approximately 5 millivolts. After the auto setup, we are now ready to perform the first measurement. So I go back to mode. I just remind you that we are in oscilloscope mode. What I will do now is I will switch the laser on. Okay, now the laser is emitting and I will start the acquisition. I'm going to see the acquisition bar moving here, and in a few seconds I will be able to see the pulses emitted by our laser. So I click fit here on the top. This is the measurement performed in oscilloscope mode. I can zoom internally, and as you can see, in oscilloscope mode I'm able to see each individual pulse. As I mentioned before, in this case I have set a repetition rate for my laser at 980 kHz. The pulse duration is 4 nanoseconds, and the average power is approximately 20 watts. I can further zoom. Now, as you can see, the rise time is very steep, while the fall time is a kind of decay. This is due to the thermal behavior of the sensor. So while the rise time can be faithful to the real time behavior of our pulse, actually the fall time here is not representative, but it represents the decay, the thermal decay time of the sensor. So in oscilloscope mode we are able to see each individual pulses, but the pulse shape that we see is not representative of the true pulse shape of our pulses, especially for short pulse duration, let's say below 100 nanoseconds. Below 100 nanoseconds, this is not representative. For very long pulses above 100 nanoseconds, this can be a good representation of the time shape of our pulses. Okay, this is the oscilloscope mode. I can now move to the real-time parameters mode by clicking here at the right the real-time parameters button, and here, as you can see on the left, I have different selection. I can measure the peak power, the energy per pulse, the frequency or the repetition rate, and the average power of our laser. In order to have these values, I just start the acquisition by pressing the start button here, and now I am measuring. As you can see here on the right, the value of the average power is displayed. It is now measuring approximately 17.7 watt, which is relatively consistent with the 20 watt that we have set in our laser system. And as you can see, we are seeing in real time the measurement, the fluctuation in the power level. Actually, I can stop the acquisition, right now, or actually I can move to the other parameter. As I mentioned, I can measure the energy per pulse by clicking energy per pulse here, click the fit measurement here. As you can read here on the right, the energy measured per pulse is approximately 18 microjoule. And here we have the behavior of the energy, the stability of the energy. I now switch to frequency or repetition rate, and as you can see here, the repetition rate of the laser is very, very stable. The system is now measuring a repetition rate of 984 kilohertz, which is very, very stable. And finally, the measurement for the peak power here and the fluctuation over time of the power. Actually, when I'm measuring in real-time parameters mode, each point displayed here is not representative of one single pulse. The real-time parameters mode is actually averaging all the pulses happening between 1 millisecond. So, for example, if I make a zoom here, each point here displayed by the software is actually not the value of the energy of an individual pulse, but it is the value of the energy over 1 millisecond. So if in 1 millisecond period of time there has been 10 different pulses, for example, this is the average of those 10 pulses between that 1 millisecond time. If we want to measure actually the energy or any of these parameters for each individual pulse, then we have to move to pulses parameter, which is here, and it is the other modality of operation. I now start the laser again. Okay, and now I start the measurement. I can see here the progress bar. Okay, I see fit here. Now, in this case, I make a zoom. Each individual pulse displayed here is actually the energy of the specific energy pulse happen in that time. The pulses parameter mode is actually a modality of operation that records and stores the instantaneous energy of the first 32,766 samples. So each one of these points is the actual energy of that specific pulse. Of course, this is true for all the other parameters in the column here on the left: energy, frequency, average power, and peak power. So, basically, the distinction, the difference between the real-time parameter mode and the pulses parameter mode is the integration time over a certain period of time, which is 1 millisecond in case of real-time parameters. In pulses parameter, we are actually measuring each individual pulse up to a maximum of 32,766 pulses per second. I go back to real-time parameters. I start again the acquisition. The real-time parameter is actually very helpful to have a very quick overview of the stability of that specific parameter over time. As you can see here at the bottom, we have also a statistics button that if we press, what we are seeing here is the peak power, the repetition rate, the energy per pulse, the sigma for the peak power, and the sigma for the energy, which are shown here at the bottom. We have also different visualization mode. I'm now in the scrolling mode. I can switch to sweeping. Sweeping means that once it has reached the end of the display, it will start again by overwriting the previous acquisition, or we can have none, in which case the acquisition will stop. So I go back to acquisition mode. Okay. Of course, the software provides the tools for saving or opening acquisition by pressing Open Save. As you can see, I can export our measurement in CSV format. I can save the image. I can open existing measurement that I have earlier performed. And I can also save some settings, the one that we have decided here for the laser type and the visualization mode here. And I can later on load a preset of those configurations by pressing Load Preset here. As I was mentioning at the beginning, this device has got trigger capabilities. Typically, we measure by setting the auto triggers, meaning that the system will determine its own triggering and perform the measurement. But there are also different modalities of operation. We can set a delay in the trigger or a pre-setting trigger, and also we can use an external trigger. We have different external triggers, both trigger in and trigger out, that can be selected on the trigger section here. And of course, we have our data log capabilities. The system is actually performing and saving in real time all the measurement performed in this directory placed on this path. Okay, now I stop the acquisition. So we are now back after the live measurement that we have performed with our new Blink HS system. We have measured a fiber laser emitting at 980 kHz with a pulse duration of 4 nanoseconds and an average power, maximum average power of approximately 20 watts. And we have also seen the Giotto software and all its capability. We are now having a quick look to the application for our Blink HS system and HSM 1000 electronics. The first application that pops to mind is the measurement of the peak-to-peak stability of our pulsed laser. As we have seen in the live demonstration, the system is capable of measuring each individual pulse, and for each individual pulse it is capable to measure the energy per pulse up to a maximum repetition rate of 1 MHz. Also, the system can measure the repetition rate, the peak power, and the average power. Being capable of measuring the energy of each individual pulse, it is possible to perform a statistical analysis of the peak-to-peak stability of our laser and calculate the sigma for this parameter. Another application is the measurement of the transient behavior of the laser, meaning more specifically to the behavior of the laser on the switch on moment. When a laser is switched on, the very first few pulses are not exactly at the full energy level that we are expecting to get from the laser according to the laser specification. For example, here we see an acquisition. Here we have the start of the laser that is zoomed here, and furthermore here, where we can easily see that the energy per pulse is increasing over time until it reaches a certain specific value, which is the operation value of the laser. This transient behavior can have different effects and can alterate the process, especially if we are running very sensitive laser process. It is sometimes useful to have information about the startup behavior of our laser. The Blink HS is capable of doing this measurement, and as it is capable to measure the energy of each single pulse starting from the very first pulse. Finally, another application is to measure the so-called burst operation. Certain lasers are capable of emitting bursts, meaning a sequence of pulses within a certain time frame. For example, here on the top, what we have seen is the oscilloscope acquisition of a burst of 4 pulses with a laser emitting at 40 MHz, meaning that the repetition rate, if we consider those pulses in the burst, is 40 MHz. Actually, the repetition rate of each burst is 500 kHz, and each individual pulse inside the burst have an energy of 8 microjoule and a pulse duration of 200 femtoseconds. So as you can see, the Blink HS sensor is so fast that it can detect each individual pulse inside the burst, even if that repetition rate would be in the range of 40 MHz. Here we have another example. In this case, the number of pulses within the burst is 15. Again, the repetition rate, if we consider each individual pulse, is 40 MHz, and the repetition rate of the burst of the pulses are 500 kHz, and each individual pulse again has an energy of approximately 8 microjoule and 200 femtoseconds. So the Blink HS is the only instrument available on the market that is capable to measure the energy of each individual pulse up to these values of repetition rate. We provide with the instrument a calibration certificate in energy, as we believe that our instrument is the new metrological standard for characterization of ultrafast lasers, down to the femtosecond pulse duration and up to the megahertz range. Thanks for your attention during this time. I'm Daniele Zanato, Sales Manager at LaserPoint. You can find my contact details here below. Please do not hesitate to contact me for any further information you might have, and I'm looking forward to see you on the next webinar we are organizing. Bye.